Hello and welcome to Tech Dictated. In the previous videos, we've looked at the SR latch. We proceeded then to the SR flip-flop, and then we proceeded to the clock JK flip-flop, and now we will be looking at the D-type flip-flop. Yeah, so when we started with the SR latch. It was quite simple, small circuit. Then we proceeded to the SR flip-flop, clocked SR latch, that is. The circuit gets bigger. And these two, okay, all these three actually are derived from the SR latch. As you can look at it, you can see the similarity. As we said before, the SR latch can either be this or the alternative circuit, which uses an OR gate. So we have the SR latch, then we have this and this and this. Okay, so all are derived. We move from this then to this, and all this are derived from this. We just modify the input such that it reduces the undetermined state. Okay, here we have the 1 1, which is undetermined, and therefore using this, when we get a 1 1, the output becomes the output goes to the input, and therefore you are able to toggle the state instead of having an invalid or unknown state. And here we avoid the 1 1 by inverting the S input. So whenever this S is a 1, this is definitely a 0. It's complement. Okay, so we never have an instance where this is 1, this input is 1 and this input is 1, because the state is always inverted when we come to this other side. Okay, so today we are looking at the D-type flip-flop. Now, as I have mentioned, this D input has an inverter. We have an inverter at the input, such that we don't have the state whereby both are 0 or both are 1. We only have a state where this is 0 and this is 1 and this is 1 and this is 0, but never any other state, because that is how we're limiting this input at the D-type flip-flop. Okay, so the D-type flip-flop stands for the data type flip-flop. The D is for the data. In the JK, I forgot to mention, JK flip-flop has no exact meaning. It just stands for the name of the maker of the type, okay, the designer, who is Jack Kilby. I think it's Jack Kilby. So that's why he used JK, just to differentiate it from the SR flip-flop. Yeah, so we have our input D, our input inverted here, or its complement here as the reset. So whenever D is 1, this is 0, and whenever this is 0, this is 1. The clock works in such a way that when this input changes, this output does not exactly change, because then it will be whenever this input changes, the output changes. Whenever the input changes, the output changes. But in order to avoid that change every single time, we have a clock in such a way that when this input changes and the clock is high, okay, it's edge triggered. Okay, the flip-flops are edge triggered, the latch is level triggered. So this is edge triggered. So whenever the input goes high, okay, edge triggered, either the positive or the negative edges. So whenever the clock goes high, then when we have an input here as high, it will be noticed. Okay, just as the JK flip-flop and the SR flip-flop. The clock is what determines whether the input is taken or what is in memory is maintained. Now let's just try it. Okay, so in this case, we only have 2 inputs. We only have actually 1 input that is being manipulated, and therefore, instead of having the 4 options or 8 options that we were having previously, now we only have 2 options. It's either a 0 or a 1, because when this is a 0, the other is a 1. When this is a 1, the other is a 0. That's just it. So let's look at it. Let me do this. Okay, so we have our clock. Let me just write it here. We have the clock. We have our D input, and we have our outputs. Okay. Yeah, let me just divide it that way. So we have, when we said it's edge triggered. So when that is low, that means the clock is 0. Okay. Then when the clock is high, that is clock is a 1. And we also have when clock is a 1. So we only have 2 instances because the input only changes at 1 point. Okay. Then we have here, it doesn't really matter what D input is because nothing will change. Then we have a 0 when the input D is 0 and when the input D is 1. Remember, when the input D is 0, S is 0, R is 1. When the input D is 1, S is 1, D is 0 because D is equal to S and is equal to the complement of R. Don't know if that makes sense, but that's it. Yeah, so now let's look at the output. Whenever we have our input as a 0, so that means here we have a 0, here we have a 1. This is a NAND gate. Let's go to our NAND gate. Whenever we have a 0, the output is a 1. Okay? Whenever we have a 0, the output is a 1. Let's assume previously what's in memory or current state, Q and Q naught. Current state is 1, 0. Let's assume that's the current state. So whenever we have our input as a 1 here, a 0 here. What have I said? Yeah, whenever we have our input D, let me just use another pen so that you can see it easily. So we have our input D as 0. That means, okay, let me just put it here. When our input D is 0, that means S is 0, R is 1. Okay. Now, when we have an input as 1, let's look at our NAND gate. 1 appears anywhere and therefore it doesn't really matter. We don't know exactly what will be here without the other output. Oh, but therefore we have a 1, 1. So our output, because the clock is a 1, So 1, 1, 1, 1, our output is 0. Then 0, 1, our output is a 1. Now, we have a 1 here and another output, a 0 here and another output that we don't know. When we have a 0, it's for sure that the output in a NAND gate is a 1. Okay? So, our output here is 1. And when we have a 1, we don't know exactly what the output is, but because this output is 1, then this is 1. And therefore 1 and 1 results to 0. Now our output is 0, 1. So, shit, I forgot. This thing really messes everything up. But anyway, I think that's understandable. So our output is 0, 1 when our input is 0, 1. Okay, so when 0, 1, our output is 0, 1. Okay, then let's go to this other state. I am going to dirtify this paper. When we have our input as a 1, now I will write somewhere else so that we don't get it all messy. Let me just write it here. So when we have our inputs here as a 1, so S is 1, R is 0, okay? It's the inverse, so R is 0. Therefore, S is 1. 1, 1, clock, okay? We have our clock here. Clock is 1 because when it's low, we maintain the state regardless of the inputs. Now, clock is also 1. Let me just put this higher. Clock is 1. So, this input results to, here at the S and clock, we have, always have this with you because it makes work easier, but you can always think about it. When we have a 1 and a 1 at an input, 1, 1 is 0, okay? 1, 0 is 1, okay? That we know. Now, we proceed. We have a 0, we have a 1. Whenever we have a 0, the output will be 1. So, therefore, Q is 1. And since we know Q, even though we don't know, now we know the output actually of this side, since we know Q. Q is the output, is the input to this other NAND gate. So therefore, we have this is 1 and 0, and this gives us 1 and 0 gives us an output. Wait a minute. Oh, sorry, the output is 1. Sorry. And this is a 0. Yeah, this is not a 0. I've confused myself. This is a 1 and a 1. Since our output was 1, our other output, because Q is 1, this will be 1. Yeah? So 1, 1 results to a 0, and therefore Q naught is a 0. And therefore here, when we have our input as 1, Q is 1 and Q naught is 0. Okay? Whenever Q is 0 and Q naught is 1, this is the reset state. And whenever Q is 1 and Q naught is 0, this is the set state. Okay? So that's what we have for our D-type flip-flop. Let me just show you when it's completed. So this is what we have. Whenever we have our clock is low, it doesn't really matter the input. The output will remain to be what is in memory. Whenever the input is high, whenever the clock is high and the input is 0, then we are resetting. Okay? Whenever the input is high and the output and the D is 1, D input is 1, we are setting. This is the D-type flip-flop. Now, I mentioned in the previous video, in a previous video, about the pre and clear. Okay, so pre and clear can be added to D-type flip-flops. It can be added to JK flip-flops, and it can also be added to the SR flip-flop. What it does is that it will override all these other ones. So whenever you're drawing that diagram and you have a pre-high, it will override all this and set it. If clear is high, it will override all inputs and reset it. It applies the same exact rule to the D-type flip-flop. Okay, whether it's JK, whether it's D, whether it's SR, whenever you have pre-high, it's setting. Whenever you have clear, it's resetting. Thank you, and let me see you in the next video.